Hello everyone, let's solve some Leetcode today. So today we have Leetcode 100, that is same tree problem. Now in this problem we will be having two trees, basically they are root nodes, and then we will have to check whether these two trees are same or not. Now here is the definition for what same means for Leetcode people. So two binary trees are considered same if they are structurally identical and their nodes have the same value. It means that even if both the trees have same node values all over the place, if they are structurally identical, then only we can say that these are same. So for example, here we have 1, then 2, and then 3, right? But then if there was a tree in which 2 and 3 nodes have switched their places, it means 2 is on the right side and 3 is on the left side, that will not be equal or same to this given tree. Now please note the word binary trees, okay? This is not a binary search tree. So this is a simple binary tree in which nodes can be anywhere. There is no rules specifying which nodes will be placed in which subtree. So nodes can be anywhere. It's just that each node will have two children nodes. That's it. So that is why you cannot just go ahead and do some traversal like in order traversal and compare that and then be like, okay, these are same because it's just simple binary tree. It's not binary search tree. So this problem can actually be solved with the help of DFS or BFS traversal. We are going to see both in this video, but DFS is usually a simpler solution. BFS is a little bit more involved solution, I would say, but you should know both of them actually, because both of them can be used in this situation, and it's a very good refresher for you to understand BFS also. So, with the help of DFS, how are we going to solve it, right? Well, we can actually start running a DFS call, okay, and in each call we will have both the nodes of these trees. In the first call we will be on this node on both the trees, okay, then we will compare if these two nodes are same or not, and then if they are same we will continue. So we will then continue and go to left nodes of both these trees at the same time. If they are equal, then great, we will continue again. We will go to the left node again, and in this case also the left node is basically null for both, so they are same, and basically since they are null and they are same, we will simply return to 2 from this point. Okay, we will not go any further. Then we will go to the right node of both the trees, so they are also null at this point. Now since they are null, we will go back to the 2, and now the 2 is done. So 2, or basically all the subtrees of 2, is basically same as this one. Simple. Now we will go back to the 1 from here at the same time, okay, for both the trees, and then we will check the right subtree. So we will go to the 3, and here since the values are same, we will say okay, continue, these are same, and then we will check both the null nodes. Since both of them are null, they are also going to be same, and so we can say okay, this is a same or basically identical tree. So we will simply return true. Now, if they were not same, suppose if this was 4, if this was 4, then you can see that at this point we would not find the same values for both of them, and if even a single node have a different structure or different value, we will simply return false. We will stop the execution right then and there and we will return false. Now, one good thing about DFS is that it is checking the structure as well as the value of the node at the same time, right? So if you are on this node for both the DFS calls, then you will be basically checking the structure plus the values at the same time. Okay, so if you go this one next to the left, you will also go to the left here also. You will check if these two are same. Since they are same, okay, great. Now at this point, we will go to the left of this one, right? And it's a null. It's null, right? And then we will go to the left of this one and it is 3. So this is null and this is 3, right? So basically they are not equal, and plus the null and the 3, which means basically existence of node and non-existence of node, is also checking whether they are identical in terms of structure or not. Okay. So the DFS solution basically checks both structure and values at the same time. Okay, that's why this solution is actually simple, because it is checking both at the same time. Now, how are you going to actually write the code for it, right? So it's a simple call. Okay, so we will simply define a function def dfs. Okay, and this function will actually take two nodes. Okay, so node 1 and node 2. Simple. Okay, and in this function, first we will check if both of the nodes are basically null. So node 1 equals none. So if this condition is true, that is both the nodes are none, so we can simply return at this point because they are both identically same, okay, in structure wise and value wise till now. So return, okay, simple return. Don't return true or false. It's just going to be a simple return, okay. If node 1 is basically null or node 2 is null, it means that then we will have to return false, okay. So here we will simply return false because we have hit this case, okay, where one was null and the other node was basically having some value or basically existing in the tree structure. So at this point, what we are saying is that these two trees are basically not identical in terms of structure at least. Maybe they are identical in terms of values, but not in terms of structure. Okay. And then the third if condition would be, so if the value of two nodes is basically different, then we will simply return false. Okay. And if all these conditions are just passing, okay, they are all fine, then we will simply go ahead and move to the next nodes, that is the left node and right node. So we will make a call for DFS. I would say node 1 dot left, and at the same time we will pass the node 2 dot left, and this is how we actually perform DFS on two trees at the same time. Then once this left subtree is done, we will again have to call the DFS for right. Now after this the function will end automatically, so this is the last line of the function, so the function will terminate automatically. So this is how the DFS function will be written, or the DFS solution will be written for this particular problem. So it's a very short code. If you understand how the DFS or basically recursion works, this code is very simple to understand, right? There are just three simple if condition and then we are just going to the left and right nodes. Simple as that. Now let us talk about the BFS solution for this problem. So how are you going to check the structure and basically the values are same for the trees, right? Well, BFS means breadth first search. So it is always going to search in levels, first level, two level, three level, four level, correct? So let's try to understand how this is going to work. So we will have two trees, correct? So in both of these trees, we will be using DFS at the same time. So both the trees will be traversed at the same time, okay? So we will have two nodes of these tree at any given instance, right? So we will have first of all this node and then this node, okay? So these two nodes will be accessed at the same time and we will check if their values are same or not. Simple, correct? Then we will go to the next level. We are not going to the next node and per se. We are simply just saying that, okay, this level is done. Okay, this is same, this level is same. Now we are going to the next level or next set of nodes. Okay, so first we are going to go here and then we will have access to these two nodes. Okay, and we can see that, okay, these two nodes are same, their values are same, correct? And then we are going to check these. Okay, these one. So 3 and 3 are same. So we can say, okay, this level is also same. Okay, got it? And then, of course, these are null nodes. So we will simply directly return till now. Okay, from here we will simply return because they are null nodes. We don't need to worry about them. But if you really notice, then you will find that there is a huge issue here. It is only checking the values of the nodes and not the structure. Let me explain what it means. Now here we have again two trees here and they are definitely not the same because their structure is different. The 4 at this point in this tree is at the left node and the 4 here is on the right node, correct? So they are definitely not the same. But when we are using BFS, we are actually maintaining a queue. Okay, so queue will be there and in this queue we will actually place the nodes, right? So there will be queue 1, then this is the queue 2. Okay, so we will be placing nodes, correct? So first when we are on this level, so we will place one here for the first queue and then we will place one here. Correct? We will traverse this node. We will cancel it out. Then first of all, once we are traversing this particular node and we see that, oh, okay, these are same, the value is same, we will take the values for its children nodes. Okay, we will take its children nodes basically, not the values only. And then we will place them in the queue. So this will become 2 comma 3, right? 2 comma 3. And remember that 1 is actually taken out of this queue now because it has been traversed. That's how BFS works, right? So now after that, we traverse this level and we see that, okay, this level is also equal as we have seen earlier, right? Now, once we have done this, first of all, when we are dealing with the 2, okay, before reaching 3, when we are dealing with the 2, okay, what we will do is we will take its children nodes and place it in the queue, okay. We will place it here. So 4 is here and the 4 is again here. and the 2 is now done. We are popping the 2 from the queue, and then only we are reaching 3, and then we are checking whether it is equal or not for both of them, right? Since the 3 does not have any children nodes, we are not putting any children node after 4 for 3, okay? So 3 will simply be popping out, okay? Now, as you can see that we have 4 here and we have 4 here. So we will just take out the 4, we will traverse this one, okay? We will see that the values are same from the queue, and we will say, okay, pop it. And here we see that we are getting into an issue that yes, there was 4 here, but the 4 was on this side, on the left side, and here it was on right side. So we did not actually have any way to check whether the 4 was structurally same or not, right? That is one issue that we are basically facing at this point, and that is exactly why it becomes important for us to actually keep track of null nodes also, because null nodes are what defines now the structure. Okay, so for example, once we have gone through the few levels, let's just create another array. Okay, let's just create queue again. Okay, so first we will have one for both of them. Okay, then the one will be popped out, and all of its children nodes will be inserted in that traversal. To 2 and 3 is inserted. Okay, so one is popped out from both the sides, and then we have 2 and 3, and then when we are on 2, okay, on 2 for both the trees, we will basically check if they are equal. So they are equal, fine, and then we will put its children nodes into the queue. So I will be putting the left first and then right. So here I will be putting 4, and then here I will be putting none, correct? The same here will not be true. So here I will be putting none and then 4. Now these two queues are no longer same. Getting it? Understanding it? How we are able to define the structure here. Now we will go to the tree, okay? And we will see that there is no children node. Yes, these 3 and these 3 are same. So values are same, but they are not children nodes. So we will not add anything into the queue. So 2 and 3 have been popped out from these stacks till now. And here now we have 4 in this queue, and we have a null node in this queue. These are not same. These are not same. So now we can say that okay, these two trees are not equal because we have found a structural difference in these two trees. So that's what makes the BFS solution a little bit more involved, because here you actually have to keep track of the null nodes also in your queue. You are basically keeping track of the structural differences in the trees on your own manually. Now, first of all, let us try to understand the BFS solution in code also. Okay, so writing this code there would just take too much time, so we will directly understand it here. First of all, we have two trees, P and Q. They are root nodes of the trees. Fine, great. We are creating a queue for both of them. So P, Q and Q, Q. Okay, simple names. Now, first of all, we will append these nodes. So the first node, okay, this one will be appended first. The one node will be appended into the queue first. So we have appended the P node for the PQ and Q node on the QQ. Okay. Then we are actually traversing or starting the traversal. Okay. It's an iterative solution. BFS is iterative. It's not recursive. So while we have values in both the queues, okay, till then we are going to run this while loop. So first we will take the element from the PQ. Okay. So P element. Then we will take the element from Q, this one. Okay. So Q element. So we have these two elements. Till now, both of them can be none, one of them can be none, or both of them might have some value which is not equal. So we are going to check. If both of them are none, okay, it means that we have reached a position where both of the nodes do not have the left node or right node. Then we just have to basically return, okay, because we cannot actually do anything in this case. But since both of them are none, okay, so as you can see that here we had 4 currently, and then we had none, okay. But in case the 4 was not here, the 4 was here in this case, then first we will actually have 4 here also, okay, and the none will be here. It's getting a little bit messy. Let me just make it better. Okay, the none will simply be shifted to this position. So at this point, this none and this none, okay, they are at the same position, right? So they will be picked at the same time from the queues. So if they are same, okay, and the same position, it simply means that okay, the structure is same and there is no node in that place, so we will simply return. There is no need to go further. Okay, it is still correct. So that's why we have this condition. Now, if any one of them is actually none, it means we have found a structural difference. So we can say that okay, these two trees are not equal, and we simply return false here. And then even if there are nodes for both of these trees, and we see that okay, their values are not equal, then clearly they are not same by value here. So we will simply return false. But if we find that okay, both the nodes are same and fine, then we will actually take the PQ, the Q for the P tree, and then append the left node of the column or the P element, and then same for the QQ, we will append the left element of the Q element, and then the right nodes for P element and Q element. Okay. So what we are doing is that at this step, first we are appending a node in the PQ like this. So we append 4 here, okay, and then in this line we are taking the q and then appending the q elements left node. Okay, so in this new we are appending the q element in this q, and then we are taking the right element of pq or p element and then appending it in the pq, and the similar for qq. So right element will be appended here, and then if they are equal, the right element will be appended here for q. If they are not equal, then of course there may be some other value in the other q. Okay, there may be none, there may be 6, there may be some other value 7. Okay, so that depends on what the values of the trees are. And if you notice, then you will realize that as soon as we find some invalid condition, we will directly return false. We will simply return false. We will not go through any more nodes. We will directly return. So it means that if this entire while loop runs, okay, without any issues, it means the trees are structurally and value wise same. So we can return true at the end of the day. Simple. Now, if we actually run it first and then we will see the DFS solution. So I will submit it. So it is pretty good in terms of time complexities. I mean, yeah, nothing runs in zero, but yeah, good enough, right? In terms of space or time complexity, so order of n is for time complexity because we are going through all the nodes, and then order of n for space complexity also because we are actually maintaining two queues for both the trees. So here is the DFS solution for the same problem. First of all, we have a res variable, that is result variable, and it will be true by default. So in case the entire thing runs without any issues, yeah, we will simply return true. Now, first of all, I am declaring the res as non-local so that we can access this variable in our DFS function as a global variable. Now, first of all, I'm checking if res is false. Okay, so if at any point in this function at a later stage or at any stage we set the res as false, then we know that these two trees are not equal. So for any other further calls, we simply say that okay, you know what? First check res. If it's false, directly return. No need to check anything else. But if it is true, as we have done this here, we check if the node 1 is none and the node 2 is none. If both of them are none, simply return, don't do anything. Okay. If node 1 is none and node 2 is none, so if any one of them is none, not both, but any one of them is none, rest will be false because structural difference we have detected, and then we will simply return. Okay. So for any further calls, the rest will be false and this condition will be true for any other DFS calls. On this line, we are checking the values of the two nodes. If they are different, we will simply set res to false again, and then we will simply return from this position. And then for any other further calls, the res will be false, so we will not compare or basically go through them. Now, if all these conditions are fine, if we have reached till here, then we will go for the left nodes for both the nodes, and then we will go for the right nodes. And then this is how the DFS will keep on working until at any stage we find the res as false. And once it is false, we will keep on returning and then we will simply return the rest at the end. So this is the function. This is the implementation for the function. And then I'm calling the DFS function with the P and Q given trees. And then after that, I'm simply returning the result. Now let's try to submit it and see how it works. So here we are getting good enough time complexity. Yeah, 0 millisecond does not make sense, but whatever. Right. And in terms of memory, we are also getting the order of n space complexity for this solution also because recursion actually creates a stack. Okay, it creates a call stack on which every DFS call will be placed. So order of n is still here for space complexity, but it's easier to handle this order of n space complexity here because of recursion. We don't have to maintain queues. So yeah, if you have any question that you would like me to target, then just let me know in the comments.